Hello everyone, welcome to my YouTube channel. In this lecture, I will show you a dynamic programming algorithm for traveling salesman problem. So in the last lecture, we solved a problem that was from a question from wait. Now I will discuss about the algorithm and the time complexity. So before begin, make sure that you have subscribed my channel and press the bell button so that you can get updated with the latest news. So let's dive into the topic. So what is traveling salesman problem? Traveling salesman problem actually is a classic optimization problem. Okay, it is a classic optimization problem. What is the goal of this optimization problem? Uh, this is actually a minimization problem. We have to find the shortest possible route that visits each city exactly once and return to the origin city. Okay, that means it will create a cycle. And we will explore dynamic programming to solve this problem. So to solve it, we have to define our base case and recurrence relation. Okay, so to solve this, we are defining a term ms, ci. S is a set, ci is ith city. This term means ms, ci means the minimum cost that start from C1. We are assuming that we are starting our journey, our tour from C1, because as this is a cycle, we can start from anywhere. So I am assuming that we are starting from C1. So is the minimum cost to start from C1? Visit all cities in set S. This is a set of cities, some cities, and end at CI. We will end our journey, our tour at CI. Then what will be the recurrence relation? The recurrence relation will be if we want to explore all the cities in S, and if we want to end our journey at CI, then we have to make a smaller subproblem. So first of all, exclude CI from this set. Exclude CI from this set. So this is a reduced problem, a smaller subproblem, right? So after that, just end our journey at CJ. CJ can be anything, but CJ is not CI. So we will calculate this term. This is a smaller problem. Then we have to go to the CI, the city, ith city, right? So we are adding D, CJ, CI. We will get this from our given matrix. We are given an input of the cost to travel from one city to another. So I hope you understand this recurrence relation. And what will be the base case? The base case is very simple. MCI, CI. We will just visit one city from C1. Okay, from C1 to C2 or C1 to C3 or C1 to C4 and so on. So this will be the distance C1 to CI for all I. This is our base case. Then what will be the what will be the algorithm? Let's go to there. This is the algorithm, okay? So we are given the set of cities and a distance matrix. The matrix have the cost to visit from one city to another city. What will be our output? Our output will be minimum cost of a tour that visits all cities exactly once and returns to the starting city. So first of all, we have to make the base case, okay? So for only cardinality 1, we will just visit one city after C1. So for 2 to Ni, we will make this array and we will initialize this array with this value because we will move from C1 to Ci, and for each Ci, we will get this. And our for loop ends here. And after that, we will solve it dynamically, right? We will use dynamic programming. So first of all, from minimum cardinality, we will go to maximum cardinality. So we will then take our set with 2, then our set size will be 3, our set size will be 4, okay? So for k is equal to 2 to k is equal to n minus 1, we will take each subset of this, of size k. Then for each ci belongs to S, we will try to end our journey at ci. How can we do this? We can do this by removing ci from the set and solve it with cj. We are ending our journey at cj, and then we will move from cj to ci, and we will take the minimum of these values, and our for loop will end here. After that, we will move to the C1 also, right? We will go to the beginning starting point again. So I'm taking the C1 in this set. We are trying to end our journey at C1. So we have already solved this term in the previous loop. Then after this, we are adding the Ci to C1, okay? And we are taking the minimum value of this. And so this will be our final output or our final result. So this was the algorithm. Then what will be the time complexity? Line 3 to 5 takes big O of n. What does it mean? Look at here. 3 to n, there is only a for loop up to n. So this will take big O of n. And line 13 takes big O of n also. What is line 30? This is line 30. Why this is big O of n? I am seeing just a one line. One line means big O of 1, right? No, because we are taking the minimum value of this. This will need another for loop to traverse each item, to traverse each ci. So c1, c2, c3, ... cn. That's why we need big O of n. And dominating part is actually step 6 to 12. Look at here, 6 to 12 is this. We are creating k size subset and solving our smaller problem. And gradually the value of k is increasing. We are solving the larger subproblem then. So the number of sets of size k is nc k. This is combination, right? Because we have n cities, we have to choose k cities, and we can choose k cities in nc k ways. And the execution time will be, we are choosing k cities, and we are traversing it. There is 2 for loops, so this will be k square, and we're trying to solve it for each size of set, right? Each cardinality of the set. First of all, the cardinality was 1, then cardinality was 2, cardinality was 3, and so on up to n minus 1. So what will be this term? By binomial theorem, we know that this term is actually 2 to the power n minus 2. So we will use this, okay? So overall time complexity will become 2 to the power n multiplied by n square. And if we can write this as big O asterisk big O of 2 to the power n, because this asterisk sign absorbs polynomial terms. So here n square is polynomial term. That's why I have removed it, and this is 2 to the power n. So why 2 to the power n square? Because there are 2 to the power n subsets. Yes, obviously. And for each subset, we need to solve for n possible n cities, and each cities involve big O of n work. That's why there is 2 loops. That's why n square, and we are choosing 2 to the power n subsets. So overall time complexity is n square 2 to the power n. If we used a brute force method, then we would need n factorial n. Why? Because n factorial means we are making permutation of the cities and calculating the costs. The permutation is n factorial, and to calculate the cost of each permutation, we will need n. So overall time complexity will become big O of n factorial n, and this is much worse, right? So our algorithm gives a very good solution and faster solution than this brute force method. So this provides our dynamic programming approach provides an exact solution of this problem. Though the time complexity is exponential, it is efficient than a naive brute force approach. This is very suitable for relatively smaller number of cities, okay? Because if our number of cities is very small, n is very small, then this will become very small, okay? So that's it for today. I hope you really enjoyed this video. If so, then press the bell button and leave a comment if you have any questions. I will try to answer those questions very fast. And if you like this video, please also share it with your friends. And that's all for today. I will again come with a new content. Till then, stay happy and be creative. And obviously, take care of your parents. So, bye bye.